Well, we got a test coming up tomorrow, and today we'll talk about what to expect. There will be 20 problems on the test. And in this unit, we looked a lot at the derivatives, the shortcuts for the derivatives, and some different forms as well. So a lot of the test will be, here's a function, find the derivative. So what you will be using with that then, of course, the power rule, product rule, quotient rule, chain rule. Those were the basic rules that we looked at. And then the next chapter, the next Think Well chapter, we looked at the specific derivatives of trig functions. And yes, you need to know those. No note cards or cheat sheets or anything. It's got to all be in your mind. So the trig derivatives, exponential derivatives. Now I will at least limit that to e as the base, e to the x or e to some power. I won't throw you a 2 to the x or anything like that. We'll get more into that later in the semester, but for now we'll just focus on the exponential, the e. And then the last special function was the logarithmic function. Logarithm. And again, there we'll just stick with the natural log, ln, not any of the other bases. But eventually we'll get back to where we're dealing with log base 2 or something like that. But now, of course, these last three, we saw those, just the basic derivative of the function. And we also saw lots of combinations of those with, well, power, product, quotient, and chain, especially the chain. Some of the problems that we worked on the worksheets, those problems are good homework problems, but they're not good test problems. I may throw you one somewhat difficult one, but I'm not going to throw you one where you have 5 chain rules in a row. But it won't be the hardest ones out of the worksheets, but maybe the medium to easy. So whatever that means. Maybe you guys think all of them were hard, but one thing that we also looked at specifically with the logarithm is changing the form of a logarithm before we take the derivative. So keep that in mind. If we have this big old nasty log, actually it'd be ln. So if we have a big ugly log function like this, well, you're going to want to simplify a little bit using the log properties before you take the derivative. And while we're at it, what would be the first thing we need to do?
Drop the 3.
Okay, exponent out in front. And technically it'd be 3 times this logarithm. And then what would we need to do? Okay, so then, now this 3 will be multiplied by the whole thing, but it'd be the natural log of the top minus the natural log of the bottom. And working through the worksheets, this seemed to be the hardest part for you guys. The algebra seems to be the hardest part. You've got the calculus down, but make sure and recognize what you can do algebraically to make the derivatives that much easier. And then from here, kind of ran out of room, but the derivative, we'd have the 3 times, well, the derivative of this would be what?
1 over log
Okay, 1 over the 3x minus 5
times 3.
times 3,
The derivative.
and then minus, derivative of this, 1 over the 2x squared minus 3x minus 1 times the derivative of that inside, which would be, what, 4x minus 3. So lots of algebraic simplifying can be done before you take the derivative, working with those logs. Try to remember to do that before you go through the derivative. Okay? Questions on these basic derivatives, and, well, maybe not so basic on some of them, but the idea of the taking the derivative, any questions, any particular problems you want to go through? In working through the test, simplifying the answers, well, it's pretty much do the calculus on it, and then do the very simple algebra. If there's some combining of like terms, do that. But if it's a fraction plus another fraction, don't worry about combining it into one fraction. If it's a binomial times a monomial, or 2 terms times 3 terms, definitely don't worry about that. But if it's just a single term, a monomial times a binomial or trinomial, you can do that pretty easily. But don't go to a lot of extensive work trying to rewrite it algebraically. Just do the really basic multiplying or combining like terms. Okay, other questions? Let's take a look at this derivative of, well, a chain rule, but with the trig functions. Now, whether it's tangent or sine, cosine, any of the trig functions, this notation means that's the power of that trig function. And for my brain, it works better if we change this, change the form to tangent of 5x quantity to the 3rd power. And that way I say, oh, okay, the cube is the outside part of it. So to do this derivative, we'll have a chain rule. Well, technically, we'll actually have 2 chain rules, but we'll get to that. The outside then will be the power. So to begin with, we'll have 3 times the tangent of 5x to the 2nd power. Okay, that'll be our derivative of the outside. Then we take the derivative of the inside. Well, again, here is where we see there's 2 different insides. The next inside would be the tangent, and then finally the very, very inside would be the 5x. So derivative of tangent is, secant squared. And what we have to remember, that's the derivative part, but we still have the 5x on the inside. Secant squared of 5x. And then finally, the last step would be what?
The derivative of the inside.
Okay, the derivative of the very inside, derivative of 5x would be 5. And then from here, let's see, there's really not a whole lot to do. I think you can handle 3 times 5, I hope. Pull your calculator out if you need to, but we'd have 15 and then times tangent squared of 5x. Go ahead and write the proper notation there since we're rewriting it. and then times secant squared of 5x. Now, whether you put parentheses around the 5x or not, either way means the same thing. You just need to recognize that 5x is the inside of tangent and the secant parts. Okay, so that would be our answer to that one. Okay, any others that types of your trig functions or exponential logarithms? Okay, now we've got the sine of pi x times the secant of pi x. Give you a workout here with your trig derivatives. What would we need to do first, though? It's in the form of a product. Okay, the sine times the secant. Okay, so start out in terms of the product rule. So we go the first times the derivative of the second. Derivative of secant is what?
I think it's secant times tangent.
Okay. And don't forget it's the secant of the inside times the tangent of the inside. And then what else do we need to do?
The derivative of the inside.
Okay. Derivative of secant pi x is technically a chain rule. And don't forget the derivative of the inside. Derivative of pi x would be pi. Pi, again, is just a number, just like the 5 was with the previous example. Pi just looks a little weird. Yep.
So you do the derivative of the inside because the pi's there.
Right.
So just X,
Right.
Like it just be 1.
Correct. It is not just secant x, it's secant of pi times x. So whether it's pi or 2x or 5x, that's a chain rule that you'll have to do the derivative of that very inside. You'll end up with a constant at the very end. Unless it would happen to be pi x squared, then you'd have 2 pi x for the derivative of the inside. But yeah, the trig functions, unless the inside is just the x, then you'll have that one extra step derivative of what's on the inside. Okay, so I guess where are we? We've got the first times the derivative of the second, and then plus the second times the derivative of the first. What's the derivative of sine?
Cosine.
Okay, is it positive or negative?
Positive.
Okay, positive. So derivative of sine is cosine of pi x. Are we done? Nope. What else? Okay, times the derivative of the very inside, so pi x, derivative is pi. And looking at this, yeah, that's about as good as you need to rewrite it. There are all kinds of trig identities that we could rewrite it in about 50 million other ways, but this is fine. Okay, questions there? Now, beyond our just basic rules and formulas for the derivative, we did have a few problems in those worksheets. Maybe evaluate, we'll use the derivative. Might be evaluate f primed of, say, 3. Well, to do that, of course, you'd be given f of x equals some function. You take the derivative, then you plug in 3 and get a value, a particular number. That would be one possible type of problem beyond just find the derivative. But using the derivative, we also looked at finding the slope of the tangent line. which turns out to be basically evaluate. You got to find your derivative first. Then, if you're given, say, some point, well, to find the slope of the tangent line, what we do in finding the slope is, well, we take the x value of the point and plug it into the derivative. So slope of the tangent line is basically evaluate the derivative function at our x value. And then beyond that, we did look at a few of find the equation of the tangent line. So in those types of problems, again, find your slope. Whatever the value of the slope is, and then plug it into the equation of a line. Some of you use the point slope form, which is fine. Say, given this point, x of 1 would be -1. I'll watch the signs. X minus -1 would actually turn into x plus 1. And then y minus 4. And then whatever your slope turns out to be. Or some of you use the slope-intercept form, which that's fine too. Should get the same answer either way. But put your slope in, whatever number you found here, and then the x, plug in -1 there, plug in 4 here, and you can calculate what b is, and then put it back in the form y equals the slope times x plus whatever the value of b you found. So either way, and leaving your answer, just give me an equation of the line. I don't need a particular form. You don't have to solve it for y to make it look really pretty like this one. If you want to, fine, but you don't have to. So some of the uses for the derivatives. Let's see, what else did we look at? Then once we kind of got the basics of that down, our next stop was the implicit differentiation. Now on these types of problems, well, we actually looked at a couple different types. Many of them involved x and y, so maybe it will be find dy by dx, given something maybe like x squared plus xy minus y cubed equals 5. Well, this is your typical one. Take the derivative with respect to x on both sides. And, well, as we go part by part, derivative of x squared would be what?
2x.
Okay. Then what do we have to do here? Okay, product rule, x times y. So the first times the derivative of the second, what's the derivative of y? Okay, in that case we got to represent the dy by dx. Then finish out the product rule. The second times the derivative of the first. Well, derivative of x with respect to x is just 1. And then minus derivative of y cubed. 3y squared
dy dx.
times the dy dx. Very good. And then derivative of 5. Okay. So the next part really would be solve for dy by dx. Here, I will require you to go ahead and go through the algebra, solving for dy by dx. We've got 2x and the y on the left side. We might as well leave those alone and move the dy by dx terms to the other side. So 2x plus y, add this one, and then subtract this one. So 3y squared dy by dx minus x dy by dx. Then factor out our dy by dx. Leaves the 3y squared minus x. And then finally divide by the 3y squared minus x. So dy by dx then will be 2x plus y all over 3y squared minus x. So there's your basic implicit differentiation problem. Then also our applying implicit differentiation, we looked at, again, what's the slope of the tangent line or what's the equation of the tangent line. Those could be possibilities given something like this. Of course, you'd also be given a particular point on the graph that you'd be able to do that for. Whatever the point is, x value, plug that in, plug in the y value, and you can calculate the slope. Okay. Now, some slight variations with the implicit differentiation. We may have a problem of find dx by dy. Well, technically in this problem, we'd be calculating the derivative with respect to y. So, let's see, we'll go. Something like that. Okay. Well, to take the derivative with respect to y, first part would be what rule?
Chain.
Okay, chain rule. We'll have 5 times the quantity to the 4th power. Simple power rule for the derivative of the outside. And then times, now be very careful here, we have 2 terms. Notation-wise, we need to put more than just this dot here. We need to put parentheses so the whole quantity is multiplied by that part. X plus y, derivative of x would be what? Okay, with respect to y, that term would be represented by dx by dy. And then the derivative of y would be what? Okay, that one would be 1 this time. Derivative of y with respect to y. So every once in a while you'll have to kind of think a little differently in terms of your variables, make sure you understand which one we're taking derivative of. And some of these equations we had other variables as well, s and t, or h and r, one of the problems. So those are usually a little easier to work with than the x and y because we almost automatically think derivative with respect to x. But read the problem carefully to know what you're taking the derivative with respect to. Okay, now we still have a little bit of work to do here. Next term, derivative of that would be what?
Minus 3 dx dy.
Okay, minus 3 dx by dy. Next part. Okay, just the 1. And then I love constants. Derivative of a constant, 0. Okay, now we've got a really interesting combination of algebra to solve for the dx by dy. We're we've got this and this. Well, this part is actually, we'll have to, there's many different ways to look at this, but probably the easiest way, this is really just a monomial, one term, because it's 5 times that quantity to the 4th power. We'll have to multiply it through these parentheses. So that times the first term plus that times 1. Thank goodness it's just 1. And then we'll have that. And once again, might be easiest to move your dx by dy terms to the other side. This is a place where you may be, it may look like you're off by a negative, but you went one direction and, well, at least on the worksheets, the answer key went the other direction. If you multiply by -1 over -1, your answer will look like the answer key. That happened in a few of those problems with the implicit differentiation, but either way is correct. So we'll leave this part on the left side and move our, add the 3 dx by dy minus 5 times that quantity. Oops. Well, it's not going to let us erase that at this point. This should be x plus y to the 4th dx by dy. And let's see. Yeah, factor that out and then divide by the 3 minus 5 to that power. Kind of running out of room here, so we'll do a quick solve. Rest of the steps. And there's your dx by dy. So again, a lot of this is just keeping in mind what are we taking the derivative with respect to, and make sure and follow that. It's not always with respect to x. Questions there? Now from here, actually, I was going to say from here we may use this to find the slope of the tangent line. If you're asked to find the slope of the tangent line or the equation of the tangent line, it's not going to be dx by dy. Slope of the tangent line means dy by dx. So the previous example, find your dy by dx, then you can find the slope of the tangent line at a particular point, plug in your x and y values. Make sure in those cases you use derivative with respect to x, not this one with respect to y. Okay. So now on the worksheet we also had find all points on the curve where the tangent line has a slope of such and such, -1 or slope of 0. I'm not going to put any of those on the test. We'll revisit that next unit, so we'll get plenty of practice on that, but won't see that on this test.
We'll see what on the test here, I'm sorry.
The applying implicit differentiation, the last couple problems were find the points where the slope equals -1 or slope equals 0. Nothing like that on this test. And finally, using the derivative, we looked at a lot of different types of problems here with position, velocity, acceleration. Given a position function, you may be asked to find the velocity, or given the velocity, find the acceleration, or some of the applications that go along with that. any of those problems from that worksheet are a possibility. Where is or given a position function, what's the maximum height? Well, maximum height, you first have to find the velocity, and then where is the velocity 0? Okay, that's where it reaches its height and then starts to fall back to the earth. And then find the time when the velocity is 0. Then the maximum height actually is plug that time back into the position function. So these types of problems, there might be about 3 or 4 particular types of problems that you have to go through before you can answer the question. So lots of different things there. How long does it take for the projectile to hit the ground? Well, in that case, that's setting your position function equal to 0. I think 1 or 2 of the problems, what's your velocity when it hits the ground? Well, that's just the next step beyond. First, you have to find how long it takes before it hits the ground, set the position function equal to 0, solve for t, and that's your time. Then plug that time into the velocity function. Okay. What is the velocity at a certain time? What is the acceleration at a certain time? So just lots and lots of different types of questions there. I'm not going to have a lot of those types of problems on the test, but probably at least 1 or 2. So, but which type? Well, you'll have to know all of them. Okay. Any of those that you'd like to see worked out? So if we have this as our position function, if we find the acceleration, well, the first thing we'd need to do is what?
Find the derivative.
Okay, derivative of p represents what?
The velocity.
Okay, that's your velocity. So v, derivative of p is what?
Negative 32 t plus 10.
Okay. And then the acceleration,
Negative 32.
okay, negative 32. Now, that's going to be the equation for the acceleration function, and it is constant, so at time 5 seconds, well, a of 5 is still going to be negative 32. Okay. Now, if there's the position functions given a little differently, then we may have a of t equals 5t minus 4. Well, then you'd have to plug in your t value and calculate. But on the vertical motion or projectile, something thrown up in the air, it's probably going to end up being the negative 32, which unit-wise would be what?
What?
What are the units on this?
Second per feet squared.
Other way.
Oh.
It'd be, yeah, feet per second squared, or per square second.
And then the velocity will be just feet.
Yeah,
Second.
velocity would be feet per second. Now, technically, the acceleration would be feet per second, but a common shortcut is just put second squared.
Oh, that makes sense.
Now, the feet is basically this. Acceleration due to gravity is negative 32 feet per second squared. Now, if it's in meters, that one is negative 9.8 meters per second squared. So your position function will probably look a little different. But I think we did 1 or 2 of those, and
And this stuff is on the test.
yeah.
Okay.
What we'll be on the test. I will give you the position function and then the units that go along with it, either where the position's in feet or meters, time. I think I always say where T is time in seconds. So, okay. Any other questions about the position, velocity, acceleration?